Hello student, today we will start magnetic force on a current carrying conductor placed in uniform magnetic field. In this topic, consider a straight conductor of length L. The length of conductor is L and area of cross section capital A. Here area of cross section is capital A. Carrying current I placed in a uniform magnetic field B. Current I in uniform magnetic field B. A current carrying conductor contains large number of free electrons. If these electrons move with drift velocity Vd and the number of free electrons per unit volume equal to small n, then the current flowing through the conductor is given by I is equal to NEA Vd. It is equation first. The direction of flow of the conventional current I is opposite to that of drift velocity of the electron. Let a conductor is situated in a uniform magnetic field at an angle theta. Clear? The magnetic Lorentz force on an electron having charge -e and moving with velocity Vd vector inside the magnetic field of strength B vector is given by F dash vector is equal to -e Vd cross B vector. It is equation 2. Clear? Each of free electron inside the conductor experiences force F vector under the effect of magnetic field. In capital N is the total number of electrons in the conductor, then force on the current carrying conductor placed inside the magnetic field is given by F vector is equal to capital N into F dash vector. It is equation 3rd. Now the total number of free electrons in the conductor, capital N into small n into volume of the conductor A into L. It is equation 4th. Substituting for capital N and F dash from equation 2 and 4 in equation 3rd, the force on the conductor F vector is equal to NAL minus E Vd vector cross B vector, or we can write F vector is equal to NEA minus L Vd vector cross B vector. It is equation 5th. Okay. If IL vector represents a current element vector in the direction of current, the vector L vector and VD vector will have opposite direction, and we can take minus L VD vector is equal to VD into L vector. Therefore, F vector is equal to NEA VD L vector cross B vector. It is equation 6. From equation 1st and 6 we get F vector is equal to I L vector cross B vector. Okay, so the magnitude of the force on the current carrying conductor is given by F is equal to BIL sin theta, where theta is the angle between the direction of magnetic field and the direction of flow of current. Okay. Next, special cases. First, if theta is equal to 0 or 180 degree, that is sin theta is equal to 0, then F is equal to BIL into 0, or F is equal to 0. It means current carrying conductor experiences no force when placed parallel or anti-parallel to the direction of magnetic field. Second case, if theta is equal to 90 degree, then F is equal to BIL sin 90 degree. Sin 90 degree 1. So F is equal to BIL, that is maximum. Okay, it means a current carrying conductor placed at right angle, means 90 degree, to the uniform magnetic field experiences maximum force. So the direction of force on a current carrying conductor placed in a perpendicular magnetic field is given by Fleming's left hand rule. Okay, so next example. First, a wire 12 cm long and carrying a current of 2 ampere is placed perpendicular to a uniform magnetic field. If a force of 0.8 Newton acts on it, calculate the value of magnetic induction. Here, solution of this example: L is equal to 12 centimeter, means 12 into 10 to the power minus 2 meter, and I is equal to 2 ampere. Okay, and F is equal to 0.8 Newton and theta given 90 degree. So using F is equal to BIL sin theta, we get B is equal to F upon IL sin theta. Put the value 0.8 upon 2 into 12 into 10 to the power minus 2 into sin 90. After calculation we will get 3.33 Tesla. Okay, so in the next topic, force between two long straight parallel current carrying conductors, or definition of ampere. In the diagram figure A, consider two long conductor A, B and C, D placed parallel to each other at a distance D apart. The current I1 and I2 are flowing through the two conductors AB and CD in the same direction. Okay, so let us find the force experienced per unit length by the current carrying conductor AB due to the magnetic field produced by the current carrying conductor CD. So the magnitude of the magnetic field at any point on the conductor AB due to current carrying conductor CD is given by, here B2 magnetic field due to current carrying wire CD. Okay, so B2 is equal to mu naught upon 4 pi into 2I2 upon D. According to the right hand thumb rule, the direction of B2 is perpendicular to the plane of the conductor AB and directed outward, means represent with dot. Okay, clear? So we know a current carrying conductor of length L placed at right angle to the magnetic field B experiences a force is given by F is equal to BIL. Therefore, force experienced per unit length of conductor AB in the magnetic field B2 due to the current carrying conductor CD is given by F1 is equal to B2 into I1 into 1. So we can write F1 is equal to B2 into I1. It is equation second. Put the value of B2 from equation first. So we get F1 is equal to mu 2 upon 4 pi 2 I1 I2 upon D. It is equation third. Okay, so according to Fleming left hand rule or right hand palm rule, to the direction of F1 lies in the plane of conductor and is directed toward the conductor CD, that is towards right, as shown in the figure. Here direction of F1 toward CD according to Fleming left hand rule or right hand palm rule. Right hand palm rule, here in this diagram Okay, if right palm is open as shown in the figure, okay, and fingers are perpendicular, fingers are perpendicular to thumb, okay, in this way that if stretched finger represent the direction of current, magnetic field B, and thumb represent direction of current, okay, I, then the force on the conductor will be perpendicular direction to the palm. Clear? Right hand palm rule clear? So next, the magnitude of magnetic field at any point on any point on the conductor CD due to current carrying in the conductor AB is given by P1 is equal to mu naught upon 4 pi into 2I1 upon D. It is equation 4. The direction of B1 vector is perpendicular to the plane of the conductor CD as shown in the diagram. Here perpendicular to the CD, okay, clear, and is directed into the plane, okay, as per right hand thumb rule. The force experienced per unit length of conductor CD in the magnetic field B1 due to the current carrying conductor AB is given by F2 is equal to B1 I2. So put the value of B1 from equation 4, mu naught upon 4 pi into 2I1 upon D into I2. It is equation 5. According to Fleming's left hand rule, the direction of F2 vector lies in the plane of the conductor and directed towards the AB as shown in the figure, towards the AB according to Fleming left hand rule, okay. Since F1 vector and F2 vector are equal and opposite, so these force pull the two conductors towards each other. Hence, we conclude the two long parallel conductors carrying currents in the same direction. Here, current in the same direction, okay. Then conductor attract each other by F1 F2 force. On the other hand, it can be easily shown that if the two parallel conductors carrying current in opposite direction as shown figure B, in opposite direction, okay, as they repel each other, F1 in this direction and F2 in this direction, okay, and the magnitude of the force experienced per unit length by one conductor due to the other conductor is same as given by the equation third and equation fifth. Clear? Next, definition of ampere. Force experienced per meter length of conductor by two parallel long straight conductor carrying current I1, I2 is given by, in general we can write F is equal to mu naught upon 4 pi into 2 I1 I2 upon D Newton per meter. If I1 is equal to I2 is equal to 1 ampere and D is equal to 1 meter, then F is equal to, put the value of mu naught, 4 pi into 10 to the power minus 7 upon 4 pi into 2 into 1 into 1 upon 1. After calculation we will get F is equal to 2 into 10 to the power minus 7 Newton per meter. Okay, thus the definition of ampere: 1 ampere is that current which, when flowing through each of the two parallel conductors of infinite length and negligible cross-sectional area and placed in free space, means vacuum, at a distance of 1 meter from each other, and produced between them a force of 2 into 10 to the power minus 7 Newton per meter of their length. Clear? That's all for today.